Hi, welcome to Modern Optimization Methods. Today we will introduce the last part of Chapter 3, the convergence rate. We will mainly focus on the convergence rate of steepest descent method, Newton's method, as well as quasi-Newton methods. Now let's first take a look at some verifications of numerical algorithms. Now remember that for algorithms, we will consider its convergence, for example, the global convergence and the local convergence. Of course, we will prefer the global convergence. Meanwhile, in terms of convergence rate, we will prefer the superlinear convergence rate or even quadratic convergence rate. However, in practice, when you want to get a good global convergence guarantees as well as a rapid rate of convergence rate, in real applications, the two aspects may not be achieved at the same time. We will talk about this later. Now, first let's take a look at the steepest descent method. To investigate its convergence rate, let's first study a very simple case, that is the quadratic function. Now let's first consider the ideal case, that where f is a quadratic function with the Hessian matrix positive definite. In other words, f takes the following form, and we have the gradient like qx minus b, and we take the line search step as the following way. Here, the line search step will be taken as the exact line search step. As we mentioned before, for quadratic function, there is explicit form for the step length. Now, let's consider the steepest descent method for quadratic function. I illustrate the performance in the following figure, where we got the contours of a quadratic function like this, and we start from the point like here. So we use the steepest descent method with exact line search. So this is the update process, and as we can see that when we go closer to the optimal solution, there is actually a zigzag phenomenon over the path. In other words, for some very bad situations, the steepest descent method may converge very slowly. Now, we check the convergence rate for quadratic function in the following way. First, let's define a special norm called the Q norm. Okay, we define the vector of x is Q norm in the following way. So it is as the square root of x transpose qx. Then after defining the Q norm, we can get the following convergence result. So we assume that we apply steepest descent method with exact line search to a quadratic function whose Hessian matrix is positive definite. Then the iteration satisfies the following inequalities. From these inequalities, we can see that the distance of the next iteration to the accumulation point x star is upper bounded by a constant multiplied by the distance of the current iteration to the accumulation point. Of course, the distance is in terms of Q norm. Moreover, let's pay more attention to this coefficient here. So this coefficient is actually a ratio between lambda n minus lambda 1 and lambda n plus minus 1. As we can see that the lambda are actually the eigenvalues of this matrix Q, and we put the lambda in the way of non-decreasing order. So lambda n is the largest eigenvalues. Now, if we look at this coefficient ratio, we can see that if all the eigenvalues they are equal to each other, then we can get the best convergence rate because lambda 1 minus lambda n is 0. In this case, we can reach the optimal solution at one iteration. However, in more cases, the lambda i's are different. Okay, so in a very bad situation, if this lambda n and lambda 1, they are far from each other, then we may get a very slow convergence rate. Now, in general, this is actually related to the condition number of the matrix Q. So we denote it as lambda n over lambda 1. So as this condition number increases, we can see that the contours of the quadratic function will become elongated. And in that case, the zigzag phenomenon will become more obvious, meaning that it takes more iterations to reach the minimum. Now, for Newton's method, let's take a look at the update first. So in Newton's method, the search direction takes the form like this. So we use the inverse of Hessian matrix multiplied by the steepest descent direction. Then with this direction, let's first make some preliminary result. So we need the assumption that if this Hessian matrix at the limit point, we denote as S star, is positive definite, then we assume further that the Hessian matrix is ellipsis continuous. In this way, we can see that when X star perturb a little bit, then in its certain neighborhood, the Hessian matrix is also positive definite. This is an important property we will use later. Now, to discuss the convergence rate of Newton's method, we need some settings. The settings include the following. We use the line search update. Okay, so notice that the update here, we use the unit step length. And for the direction, as we mentioned before, we use Newton's direction. Now, we also need some assumptions. For example, we need the function f to be twice continuously differentiable. And also, we need some information about the Hessian function. We need the Hessian matrix to be ellipsis continuous in the neighborhood of a solution X star. That's what we have discussed before. So this X star, we require that it satisfies the second order sufficient condition. In other words, we need that the gradient of f at X star to be 0 and the Hessian matrix at X star to be positive definite. So with these settings and assumptions, we have the following convergence rate result. Now we put the result in the theorem, which seems very simple. So we have, with the above settings and assumptions in the previous page actually, then there is the following result. If the starting point is closely related to X star, meaning that the starting point will lie in the neighborhood of X star, then the sequence of xk will converge to X star. This is kind of locally convergent result. Then the second result is that the rate of convergence is quadratic. So if you can see that, as we mentioned before, we want to design an algorithm with global convergence result as well as fast convergence rate. However, for Newton's method, we have local convergence result only. However, the convergence rate is fast. It is quadratic convergence. Now, to show the result, let's just give the proof in a rough idea. So by the optimatic conditions about X star, we have the following result. So we put the distance of xk plus pkn and minus x star, which is actually the distance of next iteration to the accumulation point. It can be expanded or reformulated by the following sense. So we put out an inverse of Hessian matrix at xk, and the inner part will be sort of Taylor's expansion in terms of x star. Then for the term here, we can use the Taylor's theorem, and we can get that this term actually can be bounded by the same order of the distance to the accumulation point, the second order actually. So by these two conditions here, together with the third fact that we have the Hessian matrix is non-singular at the accumulation point x star, then we can see that when xk lies between the neighborhood of x star, the inverse of Hessian matrix at sk is also non-singular and bounded. In other terms, the outside term here, this matrix is bounded and is invertible. With the condition here, then we can prove the quadratic convergence rate. So I give the rough idea here. Now, let's make some remarks about Newton's method. So in the result, as you may notice that we actually choose the unit step length in the update. Okay? So you may wonder, why do we choose the line search like the Wolf condition or others? Those line search can help us to get global convergence result actually. However, here we just mentioned the local convergence result, so we choose the unit step length. And actually, we can show that when we choose Wolf condition or other inexact line search step length, then we can prove that in the local neighborhood of x star, the unit length will always be satisfied. So this is a very special phenomenon for Newton's method. Now let's talk about the convergence rate for quasi-Newton's method. So as we recall that quasi-Newton's method is a class of directions actually. So let's first also make some settings. So firstly, we need the line search update here. Now we have the step length here, alpha k. And the direction is given by the quasi-Newton direction. And the step length alpha k, we choose Wolf conditions. Then we also have some assumptions which are similar as in Newton's method. For example, we need the twice continuously differentiable of function f. And also we assume that the Hessian matrix is ellipsis continuous in the neighborhood of x star. And this x star also needs to satisfy the second order sufficient condition. That is, the gradient to be 0 and the Hessian matrix to be positive definite. Another different assumption from Newton's method is in the third one. So we require the search condition pk needs to satisfy the following condition. This condition is actually presented as a limit form, okay? So roughly speaking, it actually means that in the limit sense, the quasi-Newton direction must behave similar as the Newton's direction, all right? So the numerator here basically says that pk in the limit sense should satisfy the first order information or should be similar to Newton's method. So with the following settings and assumptions, we can get the convergence rate for quasi-Newton's method. And it is quite short actually, and the result basically says that the unit step length is acceptable for all sufficiently large k, which is actually similar to the behavior of Newton's method. And if for some k large enough, we have unit step length, then we can achieve the superlinear convergence rate of the iterations. In other words, for quasi-Newton's method, we have also the superlinear convergence rate. Okay, so it sounds very good compared to steepest descent method. Right, let's make a brief summary about this part. In this part, we discuss the convergence rate for 3 types of methods. First is the steepest descent method. The second one is Newton's method, which have quadratically convergence rate. The third one is quasi-Newton's methods, which have superlinear convergence rate. And for the convergence rate of conjugate gradient methods, we will discuss this in chapter 5. Now, for the whole chapter, we have introduced the exact line search step and inexact line search conditions. Then after that, we introduce the convergence and convergence rate of line search methods. Okay, so this is the end of this chapter. See you next time.